A very good afternoon to everyone. This is Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology. And today we are going to discuss about energy stored and energy density in electrostatic field. So let's start. Here we can see there is a region which is free of electric fields. And let's consider there are 3-point charges Q1, Q2 and Q3. They are at infinity. Now we need to find out energy present in the system. Okay, to determine this energy present in the assembly of charge, we'll have to determine how much amount of work is necessary to assemble them. So what we will do in this region, we will bring the charges one by one. So in the beginning there is no charge present, as I said. So first we will bring charge Q1 from infinity to any point, or let us suppose point P1 in the system. So because there is no other charge present at that time when we are bringing Q1, at that time there will be no work done required to transfer Q1 from infinity to P1 because the space is initially charge free. Next, we are going to bring charge Q1 from infinity to point P2. So when we are transferring Q2 from infinity to P2, the work done will be required, which will be equals to the product of Q2 and potential V21. This potential V21 is at P2 due to Q1. Now we will bring Q3 charge from infinite to P3 position and it will be equals to Q3 V32 plus V31. So when we talk about the total work in positioning these three charges, that will be given by WE is equals to W1 plus W2 plus W3, and one by one we will put the values of all here. W1, as we said, because there was no charge present initially, so the work done was required to bring that Q1 charge from infinity to that place was 0, and remaining were due to Q2 and due to when we are bringing Q2 and Q3, the work done is Q2 V21 plus Q3 V31 plus V32. So combinedly we will write here with plus sign. So this is our equation number 1. Now if the charges are positioned in reverse order, then we can write one more equation. Still this would be 0. And this becomes Q2 V23 plus Q1 V12 and V13. Now these two equations are actually same and we can add them. So when we add both the equations, right hand side and right hand side and left hand side plus left hand side. So this WE plus WE becomes 2WE, and the further equation which we get is, and when we rearrange it in terms of Q1, Q2, Q3, we get the equation Q1 V12 plus V13 plus Q2 V21 plus V23 plus Q3 V31 plus V32. And further we can write this equation in this form. 2WE is equals to Q1 V1, where V1 is this V12 plus V13. Similarly, this can be written as V2. This can be written as V3. So finally we get this equation 2 WE is equals to Q1 V1 plus Q2 V2 plus Q3 V3. Further solving this equation, we get WE is equals to 1 by 2 Q1 V1 plus Q2 V2 plus Q3 V3, where V1, V2, V3, they are the potentials at position P1, position P2 and position P3. Now suppose if there are n point charges, here we have considered only 3, but we can write the equation, this equation for n point charges also. In that case, this equation becomes WE is equals to 1 by 2 summation of QV. Okay, and here we can take K, or we can even take N also. N is equals to 1 to N, or here we have taken K is equals to 1 to N, because we are considering if n point charges are present in the system, which needs to be brought from infinity to the points in the system. Now let us suppose if the region has the continuous charge distribution, so the summation becomes integration. So we can write the same equation for line charge, for surface charge and for volume charge. So for line charge, this equation can be written as WE is equals to 1 by 2 integration of rho L V dl. For surface charge, this equation can be written as 1 by 2 surface integration of rho S V. For volume charge, this equation can be written as 1 by 2 integration of rho V dV, rho V V dV. Now let us consider this last equation, and here in place of rho V we are putting divergence of D. It is as per Gauss law. So when we put this rho V is equals to divergence of D in this equation, we get this equation WE is equals to 1 by 2 integration of divergence of VD minus D divergence gradient D dot del V dV. Here we have an identity. We can apply this identity into this formula, and this becomes 1 by 2 integration of divergence of VD dV minus 1 by 2 integration of D dot del V dV. Now we can apply divergence theorem to this first term, and we get WE is equals to 1 by 2 integration of Vd dot ds minus 1 by 2 integration of D dot del V dV. Further we get this equation. Now if we allow the volume V to increase to all the spaces, this surface area goes to infinity, and in that case V varies as 1 by R and D varies as 1 by R square. So combinedly if we see VD, they vary as 1 by R cube, and the surface area increases as R square, and the quantity Vd dot ds, it decreases effectively as 1 by R. The surface integral goes to 0 as this R tends to infinity and S tends to infinity. So basically in this formula, this entire terms become 0. And we are left with only one term, W is equals to minus 1 by 2 integration of D dot del V dV, and here we can put E is equals to minus gradient of V. So this formula becomes further WE is equals to 1 by 2 integration of V dE dV. In place of D we can put epsilon E. Further putting it and solving it, we get 1 by 2 volume integration of epsilon naught E square. Now if we write it in this form, dWE, this becomes 1 by 2 dE dV, or it can be written as 1 by 2 epsilon E square dV. And when we differentiate it with respect to V, this becomes 1 by 2 dE, or it can also be written as 1 by 2 E epsilon naught E square. So basically this term dWE by dV is equals to small w is defined as energy density in the electrostatic field, which can be written as 1 by 2 dE or 1 by 2 epsilon naught E square, or it can also be written as D square upon 2 epsilon naught. So basically we can get one relation, WE is equals to integration of small we dV. So we can say that energy density is a quantity which when integrated on overall space yields the total energy, and all space in the volume containing the entire field. To understand this energy density and energy stored, we can take one example. So we have 3 point charges, minus 1 nanocoulomb, 4 nanocoulomb and 3 nanocoulomb, and they are located at 3 different positions, and we have to find out the total energy in the system. So by this diagram we can see that we have positioned these 3 point charges at 0, 0, 0. We have this one minus 1 nanocoulomb. At 0, 0, 1 we have 4 nanocoulomb this point, and at 1, 0, 0 we have 3 nanocoulomb charge. Now if we want to find out total energy in the system, we can use this formula WE is equals to 1 by 2 summation of QK Vk. And if we elaborate it, because only 3 charges are there, we can put the limit from 1 to 3, and this formula becomes 1 by 2 Q1 V1 plus Q2 V2 plus Q3 V3. And in this formula, we need to put the formula for V1, V2 and V3. Again, we further evaluate. So, this becomes 1 by 2 Q1 into Q2 upon 4 pi epsilon naught, and this is R, this is also R, plus Q3 upon 4 pi epsilon naught, again R. Similarly, we can write it for V2 and V3 also, and after putting the values, finally we get total energy stored in the system as 13.37 nanojoules. So that is how we can implement or we can apply this formula to find out energy in the system. In place of 3, 4, 5, 6, 7 and number of charges also can be given. At the same time, locations will be given and we can find out total energy in the system by using this formula. One more example we can take, that a charge distribution with spherical symmetry is given by this rho v, where rho naught is between 0 to r and 0 is for if the small r is less than capital R. So, we have to determine the energy stored in the region when r is less than capital R. So, we can see this is the system, this r is the radius, rho v is the volume charge density. So, when we want to find out electric field of spherical charge distribution for this region, it is given by E is equals to rho naught r upon 3 epsilon naught AR. Then we use this formula further, 1 by 2 integration of V dE dV, and we put in place of d we can write epsilon naught E. So, this formula becomes 1 by 2 integration of epsilon naught E square dV. We can put E as rho naught r upon 3 epsilon naught AR, and when we further simplify it by putting this, we get this formula. Further solving this formula and taking spherical coordinate system, we can put V is equals to r square sin theta dr d theta d phi, and after putting the limits for r, theta and phi, further solving it, finally we get this answer, We is equals to 2 pi rho naught square r to the power 5 upon 45 epsilon naught. So, that is how we can use the formulas of energy density and total energy in the system to solve the problems. So, this was about energy density in the system. In case of any doubt, please write to us. Thank you very much.